The morning of June 4th, 1944, Lieutenant Commander James Flatley pushed his F4U Corsair into a hard climbing turn above Saipan, chasing a Japanese A6M0 that had just made the mistake of engaging him at 12,000 feet. The Zero pilot was good, rolling into a vertical scissors that should have forced Flatley to overshoot. But Flatley had altitude, he had speed, and he had the most powerful fighter engine in the Pacific theater. What he didn't have was time. 3 minutes into the engagement, his oil temperature gauge crept past 200 degrees Fahrenheit. 4 minutes, 210 degrees. At 5 minutes, the needle was kissing 220, and Flatley felt the first shudder through his stick, the subtle vibration that every Corsair pilot had learned to dread. The Pratt & Whitney R2 800 double Wasp engine was cooking itself, and he had maybe 2 more minutes before catastrophic failure turned his fighter into a glider. He broke off the pursuit, dove for cooler air, and watched the Zero escape into a cloud bank. Another kill lost. Another enemy pilot who'd live to fight tomorrow because the fastest fighter in the Pacific couldn't stay in a fight long enough to finish what it started. When Flatley landed at Isley Field 20 minutes later, his oil temperature had dropped back to normal operating range, but the mission report he filed that afternoon used words that were becoming depressingly common in Marine and Navy aviation circles. Aircraft performed within specifications. Engagement terminated due to thermal limitations. The Pacific Theater in mid-1944 was supposed to be the Corsairs' proving ground, the place where Vort's bent-wing masterpiece would demonstrate the overwhelming superiority that 2,000 horsepower and 417 miles per hour promised on paper. The Marine squadrons flying from Henderson Field, Munda, and now the newly captured Marianas had been told. They were getting an aircraft that could outrun, outclimb, and outfight anything Japan could put in the air. And for the first 2 or 3 minutes of any engagement, that promise held true. The Corsair was magnificent in short bursts of violence, but air combat over the Pacific wasn't happening in short bursts anymore. The Japanese had learned brutal lessons during 1943 about engaging American fighters in quick slashing attacks. Their new tactics emphasized sustained combat, forcing American pilots to stay in the fight, burning fuel and building heat until mechanical limitations did what Japanese guns couldn't. And the Corsair's Achilles heel wasn't its guns, its armor, or its pilot. It was an oil cooling system, designed by engineers who'd never fought a 15-minute dogfight at combat power in 90-degree tropical heat. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engineering was sound on paper, almost elegant in its simplicity. The R2 800 engine, all 18 cylinders of it, arranged in 2 rows like a mechanical flower, generated tremendous power, but that power came with an equally tremendous heat signature. The engine oil wasn't just lubricant, it was the primary cooling medium for critical components. It absorbed heat from bearings, from cylinder walls, from the reduction gearbox that turned propeller shaft revolutions, and it carried that thermal load to a single oil cooler mounted in the right wing root. The cooler itself was a masterpiece of compact engineering, a core of thin aluminum fins sandwiched between inlet and outlet manifolds, positioned where airflow would be strongest during high-speed flight. In Vort's wind tunnel at Stratford, Connecticut, and during every test flight at the company's facility, the system worked flawlessly. Test pilots would run the engine at maximum continuous power for 30 minutes, 40 minutes, even an hour, and the oil temperature would stabilize at 180 to 190 degrees Fahrenheit. Perfect thermal equilibrium. What those tests never replicated was combat, not real combat, not the kind of fighting that happened over Rabaul or Truk or now Saipan, where pilots weren't flying smooth test profiles at carefully selected altitudes. They were yanking and banking, pulling 6 G-turns that loaded the engine, diving at 450 miles per hour with manifold pressure pegged, then snapping into vertical climbs that reduced airspeed to nothing while the engine continued generating maximum power. The oil cooler was designed for steady-state conditions. Combat was anything but steady state. In January, squadron commanders started noting in their after-action reports that pilots were breaking off engagements earlier than tactically optimal. The language was careful, almost apologetic. No one wanted to suggest the Corsair was deficient, but the pattern was undeniable. Engagements that lasted longer than 8 minutes saw sharply declining pilot aggressiveness. After 12 minutes, pilots were disengaging regardless of tactical situation. By March, the trend had hardened into doctrine that no one had officially written but everyone understood. Corsair pilots fought in brief, violent passes, then extended away to let their aircraft cool before re-engaging. It worked, after a fashion, but it surrendered initiative to the enemy. Japanese pilots started deliberately prolonging engagements, drawing American fighters into extended turning fights at reduced speeds where the Corsair's power advantage meant less and its cooling deficiency meant everything. Major Gregory Boyington, commanding VM F4U documented the problem with characteristic bluntness in an April 19th report to Marine Air Group 11. "The F4U is the finest fighter aircraft I have flown," he wrote, "and it will lose us the air war if we cannot keep it in the fight longer than 10 minutes at a time. Japanese pilots are not stupid. They have recognized that we cannot sustain combat, and they are exploiting that weakness systematically." The engineering officers at Vought and at the Navy's Bureau of Aeronautics reviewed the field reports with increasing concern. The oil cooling system met all specifications. It had passed every acceptance test. The problem wasn't that the system failed. It was that combat conditions exceeded the envelope of conditions the system had been designed to handle. And redesigning a cooling system for an aircraft already in mass production, with thousands of airframes either delivered or on the assembly line, would require months of engineering work, extensive testing, and modification programs that would ground squadrons for weeks. The Navy's solution was procedural rather than mechanical. In May 1944, Bureau of Aeronautics issued Technical Advisory F4U-291, which provided guidance for extended combat operations in high-temperature environments. The advisory recommended that pilots limit continuous combat to 8-minute intervals, reduce power settings when tactically feasible, and monitor oil temperature gauges continuously during engagement. It was advice that acknowledged the problem while offering no actual solution. Pilots were told to fight less aggressively to preserve their aircraft, which was roughly equivalent to telling infantrymen to shoot fewer bullets to conserve ammunition. The oil temperature problem was rooted in physics that engineering schools taught in sophomore thermodynamics courses. Heat transfer happens through 3 mechanisms: conduction, convection, and radiation. In an aircraft oil cooler, convection dominated. Hot oil flowed through the cooler's internal passages while cold air flowed across the external fins. The temperature differential between oil and air drove heat transfer, and the efficiency of that transfer depended on airflow velocity, surface area, and something called the convective heat transfer coefficient. Vaught's engineers had calculated all of this meticulously. They'd sized the oil cooler based on expected heat loads from the R2800 engine operating at maximum continuous power. They'd positioned it in the wing root, where airflow would be consistently strong. They'd used aluminum for maximum thermal conductivity. The math all worked, assuming specific flight conditions. Cruising flight at 18,000 feet, steady power settings, ambient air temperature of 15 degrees Fahrenheit at altitude. But combat over Saipan in June wasn't happening at 18,000 feet in 15-degree air. It was happening at 8,000 to 12,000 feet, where ambient temperature was 75 to 80 degrees Fahrenheit. The Corsair was fighting in air that was 60 degrees warmer than the design assumptions predicted, which meant the temperature differential between hot oil and cooling air had shrunk by 30% before the fight even started. Less differential meant less heat transfer, meant higher oil temperatures, meant earlier pilot decisions to break off combat. The other problem was airflow. The oil cooler worked beautifully at cruise speeds above 300 miles per hour, where ram air pressure forced massive volumes of air through the cooling fins. But extended dogfights didn't happen at cruise speed. They happened at maneuvering speeds, sometimes as low as 180 miles per hour during hard turning engagements. At lower speeds, the cooler received less airflow, absorbed less heat, and allowed oil temperatures to climb faster. The physics was unforgiving, and the engineering solution wasn't obvious. Technical Sergeant Michael Callahan didn't set out to solve the Navy's oil cooling problem. He set out to stop watching pilots die in aircraft that should have kept them alive. At 33 years old, Callahan was one of the senior maintenance NCOs at Marine Air Group 23, operating from Isley Field on Saipan. He'd been turning wrenches on aircraft engines since 1933, first as a civilian mechanic for Pan American Airways, then as a Marine Corps aviation specialist after Pearl Harbor. He'd maintained Wildcats, Hellcats, and now Corsairs through 2 years of Pacific combat, and he'd developed the kind of intuitive mechanical sense that comes from diagnosing 10,000 problems with nothing but hand tools and experience. Callahan understood engines the way some men understand languages, as systems with internal logic and predictable failure modes. When an oil cooling problem defied the obvious solutions, he started looking for the non-obvious ones. His investigation began with something mechanics call the hand test, a completely unscientific but remarkably effective diagnostic technique. After pilots returned from combat missions reporting high oil temperatures, Callahan would climb onto the wing and place his palm on various sections of the cowling. The engine itself radiated brutal heat, too hot to touch for more than a second, but the area around the oil cooler intake, where cool air should be rushing in to feed the cooling fins, felt wrong. It wasn't cold, it wasn't even particularly cool. It was warm, sometimes approaching ambient temperature. That observation led to the second test. Callahan borrowed a technique from automotive racing mechanics and tied strips of light cloth, basically torn-up bedsheets, to the oil cooler intake during a test flight. The cloth strips acted as crude flow visualization tools. They should have streamed straight back into the intake, indicating strong airflow. Instead, when the test pilot landed and Callahan examined the cloth, half the strips were hanging limp. Airflow into the cooler. Intake wasn't as strong as the engineering drawings suggested it should be. The problem was aerodynamic, and it took Callahan 3 days of staring at the Corsair's wing route to understand why. The oil cooler intake sat just aft of the wing's leading edge, positioned to capture air that flowed over the wing's upper surface. In smooth cruise flight, that positioning worked perfectly, but during combat maneuvering, especially during hard turning or high angle of attack flight, the airflow over the wing separated, became turbulent, lost its organized structure. Turbulent air doesn't feed into intakes efficiently. It swirls, recirculates, creates low-pressure zones that actually resist flow into the cooler. The Corsair's oil cooler was starving for air during the precise flight conditions where it most needed cooling. The engineering solution would have required relocating the intake, redesigning the ducting, probably modifying the wing structure. Months of work, thousands of engineering, at hours. Callahan had neither the authority nor the resources for that kind of modification. What he had was a completely different idea, one that attacked the problem from the opposite direction. If he couldn't get more air to the cooler, maybe he could make the existing airflow work harder. Callahan's insight came from remembering something his uncle had taught him about cooling farm tractor engines during Nebraska summers. When the tractor's radiator couldn't keep up with heat load, his uncle would add a small amount of water-wetting agent to the coolant, basically a soap that reduced surface tension and allowed water to spread more efficiently across hot metal surfaces. Better surface contact meant better heat transfer, meant cooler engines. The principle was simple. Improve the thermal interface between hot metal and cooling medium. Aircraft engine oil wasn't water, and Callahan wasn't about to start adding soap to a Pratt & Whitney R2-800. But the core principle was sound. The oil cooler's effectiveness depended on how efficiently heat moved from hot oil to aluminum cooling fins to flowing air. If he could improve any step in that thermal chain, he could increase cooling capacity without changing hardware. The weakest link in the chain wasn't the oil or the fins. It was the boundary layer of air that clung to the fin surfaces. In fluid dynamics, There's always a thin layer of stationary fluid, in this case air, that sticks to any solid surface. That boundary layer acts as thermal insulation, resisting heat transfer from the metal fin to the moving air beyond. Thinner boundary layers transfer heat better. Turbulent boundary layers transfer heat better than smooth laminar ones. If Callahan could disrupt the boundary layer, make it turbulent and thin, he could increase the cooler's heat rejection without adding more airflow. His solution was almost absurdly simple. He took a piece of safety wire, standard aircraft lock wire made of stainless steel, and wound it in a loose spiral pattern around several of the oil cooler's external fins. The wire created microscopic turbulence in the airflow across those fins, disrupting the boundary layer, inducing mixing between hot air near the fin surface and cooler air in the main flow stream. It was a tiny modification, barely visible to the eye, and according to every engineering text Callahan had ever read, it should improve convective heat transfer by somewhere between 15 and 30%. The theory was elegant. The practice was terrifying because Callahan was proposing to modify a critical engine system using materials and techniques that appeared nowhere in any technical manual. If the modification failed, if oil temperatures actually increased, or if the wire somehow damaged the cooler, he'd be responsible for losing an aircraft and possibly a pilot. And if the modification worked but couldn't be explained through official channels, he'd be admitting to unauthorized modifications that violated about 15 different regulations. He tested the concept on a single aircraft, Bureau No. 5, 7389, on June 8, 1944. The aircraft was assigned to First Lieutenant Robert Wade, a pilot who'd filed 3 separate reports about oil temperature problems during extended combat. Wade was scheduled for a routine combat air patrol the next morning, and Callahan persuaded the squadron engineering officer to let him make some minor adjustments to the oil cooler before the flight. The engineering officer, a captain named Morris, who'd learned not to ask too many questions when experienced mechanics, said they had ideas, approved the work without asking what minor adjustments actually meant. Callahan spent 2 hours that evening carefully winding safety wire around strategic sections of the oil cooler's fin array. He used 0.04-inch diameter wire, thin enough not to restrict airflow but substantial enough to create meaningful turbulence. The wire spiraled around each fin at a pitch of approximately 1 inch per revolution, creating a helical pattern that would induce mixing without causing flow separation. It was precision work, requiring careful attention to ensure the wire didn't contact any oil passages or structural members. When he finished, the modification was almost invisible, unless you knew where to look. Wade's flight on June 9th departed at 06:30 hours for a standard patrol sector north of Saipan. The mission was routine, no combat expected, but Wade took the opportunity to run some aggressive maneuvering at combat power settings, essentially stress-testing the aircraft to see if Callahan's modification made any difference. At 12,000 feet in ambient temperature of 78 degrees Fahrenheit, Wade ran the engine at maximum continuous power for 12 minutes, while executing hard turns, climbs, and simulated combat maneuvers. His oil temperature peaked at 195 degrees Fahrenheit, normal, completely within limits. Before the modification, that same flight profile would have pushed oil temps past 210 degrees within 8 minutes. Wade extended the test, staying at combat power for 18 minutes. Oil temperature climbed to 200 degrees, held steady, then actually dropped back to 197 as he entered a high-speed run that increased airflow. At 23 minutes of continuous combat power, the longest sustained high-power operation Wade had ever attempted in a Corsair, his oil temperature gauge showed 198 degrees. When Wade landed and shut down, Callahan was waiting at the aircraft with a handheld thermometer. He stuck the probe into the oil filler neck, checking actual oil temperature against what the gauge had indicated, 196 degrees. The gauge was accurate, and the oil was well below any danger threshold. Wade's comment, delivered with the dry understatement that combat pilots use when something has just saved their lives, was simple. Do this to every aircraft in the squadron. Do it tonight if possible. Callahan needed to understand why the modification worked before he could justify spreading it to other aircraft. He spent the next 2 days running calculations and consulting every thermodynamics reference he could find in the base technical library. The math confirmed what his intuition had suggested. The safety wire spirals created what aerodynamicists call a turbulence promoter, disrupting the laminar boundary layer that would otherwise insulate the cooling fins from effective heat transfer. In smooth laminar flow, air molecules near the fin surface moved slowly, creating a thermal resistance that limited heat rejection. The wire-induced turbulence mixed slow-moving air near the surface with faster-moving air further out, essentially scrubbing the fins with fresh, cool air more aggressively. The increase in convective heat transfer coefficient, the number that quantified how effectively heat moved from metal to air, was roughly 22% based on Callahan's calculations. That 22% improvement translated directly to cooler oil temperatures during sustained combat operations. There was a secondary effect that Callahan hadn't initially predicted but discovered through testing. The turbulent airflow created by the wire spirals also reduced the thickness of the thermal boundary layer downstream of each wire wrap. The cooling fins behind the wire benefited from pre-turbulated air, which meant the entire fin array downstream of each wire location experienced improved heat transfer. The effect cascaded, multiplying the benefit beyond what a simple calculation would predict. By June 13th, 8 Corsairs in VMF 223 had received the modification. By June 16th, 18 aircraft were running Callahan's wire-wrapped coolers. Each modification took approximately 90 minutes to complete, required only safety wire that was already stocked in maintenance supplies, and could be performed by any mechanic with basic skills. The technique spread through informal channels, crew chief to crew chief, squadron to squadron. Nobody filed paperwork requesting authorization because everyone involved understood that official channels would take months to approve something that needed to happen immediately. The combat results validated the modification faster than any engineering study could have. On June 20th, VMF 223 engaged a formation of Japanese A6M0s and Ki 43 Oscar fighters over Tinian in a fight that lasted 17 minutes of continuous high-intensity maneuvering. Every Corsair in the engagement was running Callahan's modified oil coolers. Not one pilot reported oil temperature problems. Not one pilot broke off combat due to thermal limitations. The squadron splashed 6 enemy aircraft confirmed with 2 more probables, and every Corsair returned to base with oil temperatures that had never exceeded 205 degrees during the entire engagement. Lieutenant Wade, who'd flown the first test aircraft, scored 2 kills during that mission and filed an after-action report that was unusually detailed about aircraft performance. "For the first time since I began flying Corsairs," he wrote, "I was able to maintain combat power throughout an entire engagement without watching my oil temperature gauge more than my gun sight. The aircraft performed exactly as designed, and I could fight the enemy instead of fighting my own equipment." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The modification was spreading across the Marianas by late June, but it remained unofficial, undocumented, and technically unauthorized. Callahan had created what amounted to underground engineering, modification, propagated through word of mouth and demonstrated through combat results rather than wind tunnel data. It worked, demonstrably and repeatedly, but it existed in a bureaucratic grey zone that made Navy engineering officers nervous and made Bureau of Aeronautics officials actively hostile. The crisis came on July 2nd when a visiting technical observer from Bureau of Aeronautics, Commander Lawrence Pritchard, was conducting routine maintenance inspections at Isley Field and noticed the safety wire modifications on multiple aircraft. Pritchard was a graduate of MIT, an experienced aeronautical engineer, and a by-the-book officer who believed that unauthorized field modifications were exactly how aircraft got lost and pilots got killed. He filed an immediate report identifying the modifications as unauthorized, unsupported by engineering analysis, and potentially dangerous due to unknown effects on oil cooler structural integrity and flow characteristics. Pritchard's report triggered an investigation that landed on the desk of Rear Admiral Calvin Durgin, commanding Fast Carrier Task Force operations in the Pacific. Durgin had the kind of problem that flag officers hate, a field modification that violated regulations but was producing measurably better combat results than factory standard equipment. He could enforce the regulations, ground every modified aircraft until the modifications were removed, and explain to pilots why they were going back to fighting with one hand tied behind their backs. Or he could acknowledge that a sergeant had out-engineered the Navy's entire aeronautical establishment and figure out how to make that official without embarrassing everyone involved. Durgin chose the third option. He ordered a controlled test comparing modified and unmodified aircraft under identical conditions, conducted by Navy test pilots who had no stake in the outcome, and documented with instrumentation that would provide data rigorous enough to either justify the modification or condemn it. The test would happen at Naval Air Station North Island in San Diego, far from combat zones, using proper engineering protocols. If the modification proved effective under controlled conditions, Durgin would authorize it formally. If it proved ineffective or dangerous, it would be banned and removed from every aircraft in the fleet. 2 Corsairs were selected for the comparison trials. Both were F4U-1, models with identical airframe hours, identical engine builds, and identical maintenance histories. Aircraft 1 received Callahan's wire wrap modification, applied exactly as he'd specified, with safety wire spirals on strategic sections of the oil cooler fin array. Aircraft 2 remained factory standard. The test profile was designed to replicate combat conditions as closely as safety regulations permitted. The test pilots would fly both aircraft through identical maneuvers at identical altitudes and power settings, while instrumentation recorded oil temperatures, oil pressures, coolant temperatures, and dozens of other parameters. The flights would happen in sequence on the same day to minimize weather variables. Each pilot would fly both aircraft to eliminate pilot technique as a variable. It was the kind of methodical engineering validation that should have happened before the Corsair ever entered service. But desperation and combat had forced innovation faster than bureaucracy could accommodate. The testing began on July 15, 1944. Lieutenant Commander Harold Eckhardt, a naval test pilot with 3,000 hours in fighter aircraft, flew the factory-standard Corsair first. His mission profile called for a climb to 15,000 feet, then 30 minutes of aggressive combat maneuvering at maximum continuous power. Hard turns, climbs, dives, high G pullouts, everything that generated heat and stressed the cooling system. The ambient temperature at 15,000 feet was 42 degrees Fahrenheit, much cooler than combat conditions over Saipan, which made the test conservative in favor of the factory configuration. After 18 minutes of combat maneuvering, Eckhardt's oil temperature reached 210 degrees Fahrenheit and was climbing steadily. At 23 minutes, the gauge showed 218 degrees. At 27 minutes, 223 degrees. Eckhardt terminated the test at 29 minutes, when oil temperature touched 226 degrees, approaching the maximum allowable limit of 230 degrees. The factory standard cooler was adequate for the test profile, barely, and only because the ambient temperature was 30 degrees cooler than actual combat conditions. 2 hours later, after the engine had cooled completely, Eckhardt flew the modified aircraft through the identical profile. Same altitude, same power settings, same maneuvers, same sequence. After 18 minutes, his oil temperature gauge read 192 degrees Fahrenheit. 28 degrees cooler than the unmodified aircraft at the same point in the test. At 23 minutes, 197 degrees. At 29 minutes, when Eckhardt would have terminated the factory standard test due to high temperatures, the modified aircraft was showing 202 degrees and holding steady. Eckhardt extended the test, continuing combat maneuvering for 43 minutes of continuous maximum power operations. Oil temperature peaked at 208 degrees at the 37-minute mark, then stabilized at 206 degrees and remained there for the final 6 minutes of the test. The The modified cooler was rejecting heat fast enough to maintain thermal equilibrium during sustained combat operations that would have cooked the factory standard system. The instrumentation data told the complete story. The wire-wrapped cooler was transferring approximately 24% more heat than the standard cooler under identical conditions. The modification had increased the cooler's effectiveness without changing its size, weight, or drag characteristics. It was, in engineering terms, a free lunch, the rarest and most valuable kind of innovation. Commander Pritchard, the same officer who'd filed the initial complaint about unauthorized modifications, conducted the post-flight analysis and wrote the engineering summary. His report acknowledged that the wire-wrap modification produced measurable, significant, and consistent improvement in oil cooling capacity. The modification involved negligible cost, required no special tools or materials, could be implemented by squadron-level maintenance personnel, and showed no indication of structural problems or unintended side effects. His recommendation was immediate fleet-wide implementation. The Navy's Bureau of Aeronautics issued Technical Directive F4U-318 on August 3, 1944, officially authorizing the oil cooler wire wrap modification for all F4U variants. The directive included detailed specifications for wire diameter, spiral pitch, and installation locations, all taken directly from Callahan's original work. It mandated that all Corsairs in forward areas receive the modification within 30 days, and that all aircraft still in production or depot-level maintenance incorporate the modification as standard equipment. Vought aircraft received a contract modification requiring them to implement the wire-wrap cooling enhancement on all Corsairs rolling off the production lines at Stratford and Dallas. Hamilton Standard, which manufactured the oil coolers as a subcontractor, revised their manufacturing specifications to include the turbulence-promoting wire wraps as part of the base cooler design. By September 1944, every Corsair reaching the fleet had Callahan's modification built in from the factory. The combat impact was immediate and profound. Corsair squadrons that had been limited to 8 to 10-minute combat engagements could now sustain maximum power operations for 25 to 30 minutes without thermal concerns. Pilots who'd spent months managing oil temperatures could focus entirely on fighting the enemy. The tactical flexibility this created was transformative. Marine squadrons over Peleliu in September demonstrated the new capabilities during an engagement on September 17th. 12 Corsairs from F114 intercepted 18 Japanese fighters attempting to strafe American landing forces. The engagement lasted 22 minutes of continuous high-intensity combat. Every Corsair maintained maximum power throughout the entire fight. The Marines splashed 13 enemy aircraft, confirmed with 3 probables. 1 Corsair took battle damage, but all returned to base. Not one pilot reported any oil temperature issues. The kill ratios told the larger story. In June 1944, before widespread adoption of the modification, Corsair squadrons in the Pacific posted kill ratios averaging 8-1 against Japanese aircraft. By October, after fleet-wide implementation, that ratio had climbed to 12-1. Some of the improvement came from declining Japanese pilot quality and deteriorating enemy logistics, but the sustained combat capability provided by effective oil cooling was fundamental. Corsairs could stay in fights longer, pursue damaged enemies further, and maintain air superiority over target areas for extended periods. The modification's success created an interesting problem for the Navy's official narrative. Bureau of Aeronautics had spent millions of dollars designing the Corsair's cooling system. Vaught's engineers had conducted extensive analysis and testing. The aircraft had passed rigorous acceptance trials. Now, a maintenance sergeant using standard safety wire had improved the system's performance by 24%, with a modification that cost roughly 12 cents per aircraft and could be installed in 90 minutes. The official acknowledgement came in the form of Technical Directive F4U-318, which documented the modification without explaining its origin. The directive's introduction stated that recent field experience has identified opportunities to enhance oil cooling system performance through improved fin turbulation. It was bureaucratic language that avoided saying a sergeant had out-engineered the entire aeronautical establishment, but anyone who read between the lines understood exactly what had happened. Technical Sergeant Michael Callahan received no medal, no commendation, no formal recognition for solving a problem that had been costing lives and compromising combat effectiveness. The Marine Corps didn't award decorations for maintenance innovations, no matter how significant, but he received something more valuable than a medal. On September 28, 1944, he received orders transferring him to the Naval Air Test Center at Patuxent River, Maryland, with duty assignment to the Engineering Test Division. The transfer was highly unusual. Enlisted personnel, even senior NCOs, rarely received assignments to test centers where engineers and test pilots dominated the culture. But Admiral Durgin had personally requested the transfer, arguing that the Navy needed people who could see problems that engineers missed and solve them with practical solutions rather than theoretical analysis. Callahan spent the remainder of the war at Patuxent River, working on cooling system improvements, hydraulic modifications, and dozens of other field-identified problems that needed someone who understood both engineering principles and maintenance reality. His oil cooler modification lived on through multiple aircraft generations. The Korean War-era Corsairs, F4U-4 and -5 models that fought over the frozen hills of the peninsula, used refined versions of the wire wrap technique. The technique appeared in Navy maintenance manuals for other aircraft types, usually without attribution, as standard practice for improving air-cooled heat exchanger performance. Jet aircraft in the 1950s used variations of the same turbulence-promoting principle in their oil coolers and fuel-air heat exchangers. By the time Callahan retired from the Marine Corps in 1953 as a Master Sergeant, his modification had been incorporated into oil cooling systems for everything from fighter aircraft to patrol bombers to helicopters. The principle had become so standard that most engineers using it had no idea where it originated. It was just accepted practice, one of those engineering tricks that everyone knows without anyone remembering who figured it out first. The historical record on Callahan's modification is surprisingly sparse. The after-action reports from June and July 1944 mention improved oil cooling performance, but rarely specify the source. Technical Directive F4U-318 documents the modification, but doesn't name its inventor. Callahan's own personnel file shows his transfer to Patuxent River, but doesn't explain why a maintenance sergeant received such an unusual assignment. The connection between the man and the innovation exists primarily in squadron histories and in the memories of pilots who flew Corsairs with modified oil coolers and wondered why their aircraft suddenly performed better than the one their training squadrons had flown. The broader lesson about field modifications and institutional knowledge remained contentious throughout the war and beyond. The Navy wanted standardization, controlled testing, and engineering validation before any change to aircraft systems. That approach ensured safety and prevented well-intentioned but dangerous modifications from reaching the fleet. But it also meant that solutions to real problems had to navigate months of bureaucratic process while pilots continued flying with deficient equipment. Callahan's modification worked because it was technically sound, properly tested in combat conditions, and spread through informal networks that allowed rapid iteration and validation. It could have failed catastrophically if the physics had been wrong or if the implementation had damaged cooler structures. The fact that it succeeded doesn't prove that bypassing official channels was the right approach. It proves that sometimes the gap between engineering theory and combat reality is so large that waiting for official solutions costs more lives than taking calculated risks. The Corsairs' combat record speaks for itself. Between 1943 and 1945, F4U squadrons shot down over 2,000 Japanese aircraft against combat losses of only 189 Corsairs lost to all causes, including ground fire and accidents. The kill ratio of better than 11-1 made the Corsair the most successful fighter aircraft in the Pacific theater. That success came from multiple factors: powerful engines, rugged construction, excellent pilot training, and declining Japanese capabilities as the war progressed. But sustained combat capability, the ability to stay in the fight for 20 or 30 minutes at maximum power without thermal limitations, was fundamental to everything else. Pilots with confidence in their equipment fought more aggressively. Squadrons that could maintain air superiority over target areas for extended periods provided better support to ground forces. The tactical flexibility that came from reliable cooling allowed commanders to use Corsairs in roles that would have been impossible with the factory-standard thermal limitations. Lieutenant Commander James Flatley, the pilot who'd broken off a pursuit over Saipan in June due to oil temperature concerns, shot down 3 Japanese aircraft in a single engagement over Iwo Jima in February 1945. The engagement lasted 19 minutes. His oil temperature never exceeded 204 degrees. In his after-action report, Flatley noted simply that aircraft performance was excellent throughout extended combat operations. He didn't mention oil cooling, didn't mention wire-wrapped fins, didn't mention that his aircraft could do something that would have been impossible 8 months earlier. That's how the best field modifications work. They become invisible. They stop being innovations and become standard equipment, so thoroughly integrated into the baseline that nobody remembers there was ever a problem. New pilots climbing into Corsairs in 1945 had no idea that the oil coolers in their aircraft incorporated a modification developed by a sergeant with a spool of safety wire and a basic understanding of thermodynamics. They just knew their aircraft worked reliably and consistently, even during the most demanding combat operations. The oil cooler modification represented something larger than a technical fix. It represented the reality that engineering happens in layers. The formal engineering that happens in design bureaus and wind tunnels creates the foundation, the 95% of an aircraft that works correctly the first time. But the final 5%, the adaptations and optimizations that make the difference between adequate and excellent, often comes from the people closest to the actual operating conditions. Mechanics see problems that engineers miss because mechanics see the problems daily, repeatedly, under the full range of conditions that aircraft actually experience. They see the patterns, the consistent failure modes, the situations where specifications don't match reality. When organizations create channels for that field knowledge to flow back to designers, when they value empirical observation as much as theoretical calculation, they get aircraft that perform better than the sum of their engineering specifications. Callahan's modification cost 12 cents per aircraft and improved cooling capacity by 24%. That return on investment, measured in either financial terms or combat effectiveness, is almost impossible to match through conventional engineering development. It worked because the problem was correctly identified, the solution was physically sound, and the implementation was carefully executed. It could have failed for any number of reasons, but it didn't fail because Callahan understood both the physics and the practical constraints well enough to find the narrow path between innovation and recklessness. The Marine Corps eventually recognized Callahan's contribution, though the recognition came decades after the events. In 1978, the Marine Corps Aviation Association published a history of maintenance innovations during World War II, and Callahan's oil cooler modification received a 3-page chapter written by a retired colonel who'd flown Corsairs in VMF 223. The chapter included interviews with Callahan, who was 71 years old and living in Oregon, working as a technical consultant for a small aviation company. When asked about the modification and its impact, Callahan's response was characteristic of the generation that fought the war without expecting recognition for doing their jobs. "We had pilots dying because equipment wasn't working right," he said. "I had an idea that might help. I tested it carefully, and it worked. That's what mechanics do. We fix things. The only surprise was that it took so long for anyone to ask if there was a better way to cool the oil." The interview revealed one other detail that never made it into official records. Callahan had proposed essentially the same modification to improve oil cooling on Wildcat fighters in 1942, early in the Pacific Campaign. He'd submitted a formal suggestion through improper channels, documented with calculations and diagrams. The suggestion had been reviewed by engineering officers at Marine Air Group 23, forwarded to Bureau of Aeronautics for evaluation, and eventually rejected with a note saying that field modifications to cooling systems were not authorized and that the factory-designed systems were adequate for operational requirements. Callahan kept the rejection letter. When he finally implemented the same basic idea on Corsairs 2 years later, he didn't bother with formal channels. He just did the work, tested it carefully, documented the results, and let the performance speak for itself. By the time official channels caught up, the modification had already proven its value in the most rigorous testing environment possible: sustained combat against an enemy who killed you if your equipment failed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.